Now I'm going to discuss about the packing efficiency of solid state. Packing efficiency or packing fraction, which I've been talking earlier in the video prior to this. Packing efficiency or packing fraction. Now, this is a very simple thing which you're going to learn over here. However, several questions, are asked from this particular part of the chapter. So we are going to learn how to find the packing efficiency of a unit cell. What it means is, you can imagine there to be a box, cubicle in nature, and what we are going to do is the number of spherical balls you will be able to insert into this particular cubicle box. So more the number of balls you can pack into this particular box, the more efficient it is. So same way here, instead of the spherical balls we have atoms, and instead of the box we have the unit cell. In fact, it looks like a box only, except this time the length, breadth and height is same. So for solid state, what we are going to do is, we are going to understand that how efficiently we'll be able to have atoms inserted into a unit cell. So before getting deeper into this, what we are going to do is we are going to learn the formula for packing efficiency. Before learning the formula for packing efficiency, we are going to learn about packing fraction first. Packing fraction is equal to volume occupied by atoms. So the volume occupied by atoms inside the unit cell divided by volume of the unit cell. And packing efficiency is simply the percentage. That means per 100. So packing fraction multiplied by 100. This will give me the packing efficiency. Of course, the answer will be in the form of percentage. This won't have any unit because it's a ratio between the volume occupied by atoms divided by volume of the unit cell. Both are volumes, so therefore the units will get cancelled. So packing fraction is a pure ratio, whereas packing efficiency is in percentage. So this is what we are going to calculate for each of the different type of unit cells which we have learned. So first of all, we are going to begin with the simple cubic unit cell. So first of all, we are going to find the packing efficiency of simple cubic unit cell. So we are going to find the packing efficiency of simple cubic unit cell. Now, first of all, let's get back to what we had done earlier, where I am repeatedly doing the same thing so that you get it inside your head. You don't need to mug it up much. Here, I'm going to take a unit cell, a cubic unit cell, a simple cubic unit cell. So I've taken a simple cubic unit cell, and I believe you remember, in a cubic unit cell, we have atoms at the corner. So here it is. Now let's assume the edge length to be A, and let me write, there are certain things. So edge length is equal to A. We have taken it as A, volume of unit cell Since it's a cubic cell, it's a cube, so side into side into side. So we have A cube. And what is the volume of a single atom? Of an atom. Now remember, an atom is in the form of a sphere. So if this is the radius, what is the formula? The formula is the volume of a sphere, that is 4 by 3 pi r cube. So that's the volume of an atom. And what else do we require? We require the relationship between the edge and the radius of the atom, which we have found it in the prior video. Relationship between A and R, and it is A equal to twice of R. We have already found this. I have showed this to you before this, and we have the rank as 1. So these are few parameters which we require for calculating the packing efficiency of simple cubic unit cell. So what do we get? Packing efficiency. First of all, we'll find the packing fraction. Volume of atoms. So divided by volume of the unit cell. So what is the volume of the unit cell? I am writing the denominator before. What is the volume of the unit cell? That is A cube. And what is the volume of atoms over here? Here we have altogether the rank of this particular unit cell is 1. So what does it mean? It means that there is simply, we can assume that there is simply one atom which is packed inside this particular unit cell. So 1 into volume of an atom. So what is the volume of an atom? That is 4 by 3 pi r cube. Now what do we have? 4 by 3 pi r cube, and A cube is how much? A cube is 2r whole cube. I am substituting the value of A with 2r because that is the relationship which we have found, and you will come across this, that is pi divided by 6. This is equal to 3.14 divided by 6 equal to 0.52. So that's the packing fraction. To get the packing efficiency, simply multiply by 100. So 0.52 into 100, we get 52%. And what percentage of empty space do we have over here? We have 100 minus 52, that is 48%. This particular thing is technically called voids. So voids is 48%. That is the amount of space which is empty. So that is how we calculate the packing efficiency of a simple cubic unit cell. Isn't it very easy? Now what we are going to do is we are going to find the packing efficiency of a body-centered cubic unit cell. So I'm going to discuss about the packing efficiency of body-centered cubic unit cell. So once again I'm going to draw this so that don't forget it. Though we have already found the rank and the edge length, all this values we have already found before this. I've already taught you how to do that. So at the corners we have it as usual, just like a simple cubic unit cell. Along with that we have it at the center. So let this be the center. So inside the body of the unit cell we have the atom over here. So we are going to write with respect to a body centered cubic unit cell the values of this, which will require for calculating the packing efficiency and packing fraction. So edge length naturally we have taken it as A. So this length we have taken it as A. So edge length is A. So volume of the unit cell, since it's a cube, it will be A cube definitely. And then what do we have? Volume of an atom. Since an atom is a sphere, we have taken the formula of the sphere out here, 4 by 3 pi r cube. Now here what we have is the relationship between A and R, that is edge length and the radius of an atom. So I have already showed this to you. A is equal to 4r divided by root 3. I believe you remember. This was in the video previous to this. And what is the rank of the body-centered cubic unit cell? That is 2. So here we are going to find the packing fraction first. Packing fraction is the volume of the atoms present in that particular unit cell. So what is the rank? The rank is 2 multiplied by volume of an atom, that is 4 by 3 pi r cube divided by volume of the unit cell, that is A cube. Now substituting the value of A, we are going to substitute, that is 4r by root 3. So we get 2 into 4 by 3 pi r cube divided by 4r root 3 whole cube. So what do we get? Ultimately we are going to get pi into root 3 divided by 8. So we get, let me write it here, 3.14 into root 3 divided by 8 is equal to 0.68. So to calculate the packing efficiency, we get is multiplied by 100, 0.68 into 100, we get 68%. And voids, that is the amount of free space, is 100 minus 68, that is 32%. And finally, we are going to see the packing efficiency of face-centered cubic unit cell. So this time I am going to calculate the packing efficiency of face-centered cubic unit cell. Here is the cubic unit cell, and remember, in face-centered cubic unit cell you will have an atom at the middle of each face. There are 6 faces, so you will have atom at the middle of every face. So at the top, at the bottom, at the 2 sides, and then at the front, at the back. So we have 6 atoms. Now we have assumed the edge length to be A as usual, just like before. The volume of the unit cell, since it's a cube, it's A cube. Volume of an atom, since an atom we are assuming it to be in the form of a sphere, so it is 4 by 3 pi r cube. And here what we require is the relationship between A and R, that is the edge length and the radius. And what is the relationship? A is equal to 4r divided by root 2. So 4r divided by root 2 is the relationship between A and R. And rank is 4. This will make it highly efficient. You will see it just now. Now we are going to find the packing fraction. And how do we find the packing fraction? That is the volume of atoms in the unit cell. So the rank is 4 multiplied by the volume of a particular atom, that is 4 by 3 pi r cube divided by A cube, that is volume of the unit cell. Now we are going to substitute the value of A with this, 4 into 4 by 3 pi r cube, and A cube is 4r by root 2 whole cube. So how much do we get? We get ultimately, you can check this out, pi by root 2 into 3. So how much do we get? 3.14 divided by root 2 into 3 is equal to 0.74. So we get 0.74, and the packing efficiency will be, of course, 0.74 in percentage multiplied by 100. We have 74%. And voids, that is the amount of free space, is 26%. That's it. Isn't it very simple? Finding the packing efficiency of the different unit cell. Thank you. Hope we are going to see you all in the next lesson.